Now that we know how to determine when a function is increasing and decreasing, now we want to say, okay, well, what's happening at that critical point? So if I know it's increasing before the critical point and decreasing after, what's actually happening at that critical point? Well, there's three options. If we have a critical point, we can either have a relative maximum, a relative minimum, and so now I'm on an open interval, because remember, on a closed interval, we have absolute. So on an open interval, I can have a relative minimum, a relative maximum. Remember, local minimum and local maximum are also words that are used for that. Or I could have neither happening. For example, if you think about a critical point occurs when my slope or my derivative is 0. So just isolating this third one, and we're going to look a lot more in depth at 1 and 2. If, for example, I have x cubed, I know that x cubed looks something like this. So I know my derivative is 0, but I do not have a maximum or minimum. So what we're going to say is that if our slope changes from negative to positive, so from decreasing to increasing, I should have a relative minimum. If it changes from positive, so increasing to decreasing, I should have a relative maximum. Again, a relative or local minimum or maximum is just going to be a hill or a valley. Let's go ahead and look at some of these. So the way I'm going to handle this first derivative test to figure out where my relative minimums and maximums are is by setting up a table. So very similar to the one I set up for increasing and decreasing, but I'm going to take it a step further. So I'm going to start by finding my derivative. I'm using this power rule here. So I just get 2x plus 6. Finding my critical numbers, I set my derivative equal to 0. Since it's linear, I can subtract 6 and divide by 2 to get only one critical value at negative 3. Since I'm not given an interval, I can assume it's an open interval across the domain. Of course, the domain of a polynomial is all real numbers. And I'm going to go ahead and say that my interval goes from negative infinity up to negative 3, from negative 3 up to positive infinity. So again, setting up those intervals using my critical point. So that was my, and I'm going to erase this so I can label what I've got going on here. I'm going to change colors. So my interval, so from negative infinity to negative 3, and from negative 3 to infinity. After I got my interval, I'm going to go ahead and pick a test point. So I'm going to go ahead and say negative 4 and 0. I use 0 whenever I can. 0 is typically pretty easy to work with. Then I'm going to go ahead and say, what is the sign of my test point, and I'm going to call it a TP, being plugged into my derivative? Well, when I plug negative 4 into my derivative, I get negative 8 plus 6. Well, that's going to be negative, so I'm going to go ahead and say that my sign is negative here. When I plug 0 in, I get 0 plus 6, so this is going to be positive. And so I can determine that I'm increasing, or excuse me, I'm not increasing, I'm decreasing from negative infinity to negative 3, and I'm increasing from negative 3 to infinity. So if I go from decreasing to now all of a sudden increasing, notice I'm going to have a low point. So I'm going to go ahead and say that I'm going to have a relative minimum at the point negative 3. Well, I have to figure out what y value corresponds with that negative 3. Well, to find a y value, I have to go back to my original function. So I use my calculator, I put negative 3 in, and I get 8. And it doesn't look like I have a relative maximum at all. Going on to the next one, there are only 2 examples on this. If you feel comfortable, go ahead and try this one. I know I've only given you one example on it, so you might just want to follow along and wait to try some practice in class. So I'm going to have to use my quotient rule. So setting up my quotient rule, and then I can go ahead and say my derivative, first times the second, minus 2x cubed, all over the second squared. Now I'm just going to go ahead and clean this up. I'll distribute. My 2x cubes cancel, so I'm left with, I'm going to go ahead and set my derivative to 0 because I know I'm going to find my critical points, negative 18x over x squared minus 9 all squared. So remember, when finding my critical points occur wherever the derivative is 0 or it does not exist. Well, if I have a fraction, I know it's 0 whenever the numerator is 0. So it looks like x equals 0 would make my numerator 0. I know it doesn't exist whenever my denominator is 0. So if I think about what would make this 0, well, whatever values would give me x squared minus 9 to be 0. Well, I know 3 squared minus 9 is 0. I also know that negative 3 squared minus 9 is 0. So I'm going to go ahead and say that x is negative 3 and x is 3. I'm going to use all three of these to set up my interval. So when I set up my interval, again, it's an open interval. I was not given a closed interval. I'm going to go from negative infinity up to, not to 0, to negative 3. I always want to go in numerical order, so negative 3 does come before 0 when reading from left to right. Then I'll pick back up from negative 3 to 0, from 0 to 3, and then I always finish by going up to infinity. So then from there, I'm going to go ahead and pick a test point in each interval. So let's say I say negative 4, I say negative 1, I say 1, and I say positive 4. Then I'm going to find the sign, positive or negative, of f prime of my test point, which I'm going to call TP. Well, when I plug negative 4 into my derivative, I'm going to get a positive on top, so I'm going to make a little note of that. And on the bottom, notice my bottom's always going to be negative. So regardless, or excuse me, always going to be positive. Regardless of what I get here, once I square it, it's going to be positive. So I'll have a positive over a positive, which is a positive. When I plug in negative 1, it's positive on top. Again, my bottom is always positive in this one. So I still am positive. When I plug in a 1, I get a negative on top, still a positive on the bottom. Well, negative over positive is negative. Plugging in a 4, I get a negative on top and a positive on the bottom, which gives me negative. So I can go ahead and say I'm increasing here all the way from negative 3 to 0, and I'm decreasing here all the way from 0 to infinity. Now, as you've seen before, for example, if you think of something as basic as a linear function is always either increasing or decreasing. So I do not have to change from increasing to decreasing or from decreasing to increasing. I can be 1 all the way across. So notice that nothing's happening at negative 3 because I'm remaining increasing, and nothing's happening at 3 because I'm remaining decreasing. But here at 0, I'm changing from increasing to decreasing, so it looks like I have a hill. So since I have a hill, I'm going to go ahead and say I have a relative or a local maximum at the point 0, comma, and to figure out 0 what, I go back to my original function. So I'll get 0 over 0 minus 9, and I get just 0. Now, oftentimes, these two functions only had one. One of them had a relative minimum, the other one had a relative maximum. Oftentimes, you're going to find that these other critical values do yield other maximums and minimums, or relative maximums and minimums. So don't feel as though you can only get one. You can get 1, you can get 2, you can get 3. There really is no limit to how many relative maximums and minimums you can get. Bring these notes with you to class. Let me know if you have any questions. Otherwise, you can just use them as a tool when you're doing your practice.